Hey folks, welcome back to our channel. My name is Nigel and this is my dad, Roger. And this is Offgrid Van Life, where we look at van conversions, lithium iron phosphate batteries, and Offgrid Power. Basically, we want to help you to be able to convert vans, get on the road, find adventure, and have an awesome electrical system so that you can do whatever you want to with your van, whether that's running a coffee machine, playing a PlayStation in your van, running a TV, whatever it is. We want you to be able to do that while you are on an adventure. And so in this video, this is part of our series of converting the Nissan van. And obviously I'm not in our Northern Ireland workshop or working on that van currently, but I'm over in our England workshop here with my dad. And what we're going to be doing today is to build out the battery system for the Nissan van. So I've spoken a little bit in this series about what the plans are with the van, in the sense that we're going to be putting in a very substantial lithium iron phosphate battery system, and we're going to be running the van on single fuel and electric. So all the heating is going to be done with the diesel heater and everything else is going to be done with electric. So lights, charging, all that sort of stuff. And we're also going to be cooking on electric. So we're going to be putting in a very substantial lithium iron phosphate battery that's going to run a very substantial 3 kilowatt inverter, and that's going to run an induction cooktop and an electrical oven as well, and obviously fridge and all the other stuff that goes with it. But yeah, so that's what we're going to be doing in this video. Is we're going to be building out a 2S4P battery system, which is going to be like a
2P4S.
2P4S. I always get the things wrong. 2P4S. So it's basically 8 cells configured in a 12-volt configuration, which will give us, I think, 500 or 600.
560, of which about 500 will be usable.
Yeah. So
but the challenge is we don't want to change from a 12 to a 24-volt system, because that just adds complexity, and you have to have a charger that comes from a 12-volt alternator to up to 24-volt to charge it, and then back down to 12 for all the house electrics and that.
Yeah. And so if the vehicle was already a 24-volt electrical system, it would make sense to configure it in 24 volts, because then obviously your amperage is lower for your inverter and all that sort of stuff. But given that the vehicle is 12 volts, we just figured it would be easier to keep it in 12 volts, but we want a really substantial capacity. So that's why we're building out 560 amp hours, of which about 500 usable amp hours. But it's going to be very substantial to allow us to be able to cook on an induction, all that sort of stuff. So yeah, we're going to crack on with it now. So we're going to be building out the battery case, charging up, top balancing the cells, configuring it, getting it all together. We're going to have to custom make some flexible bus bars for the battery. And then once it's all configured, we're going to connect up the inverter and actually do some tests in this video over the next couple of days. And we'll take you on that process. So we'll show you how it does and what the tests look like.
Yeah, just a little bit more in our thinking is that to carry more than 200 amps on a 12-volt battery is asking a lot. Things are going to get really hot. That's why we're going for a 2P4S, because we essentially have 2 batteries. It's like having 2 batteries. We'll have 2 sets of 4 cells making up 8 cells, and each set will be essentially carrying 150 amps at the most.
Yeah.
And that is doable. That's fine. 12 volt can cope with that. And the BMS, which is the Daly 300 amp BMS, has 2 cables coming out to attach to the battery, and then 2 going out to your negative. And so using both of those, we'll connect to, one to each of the sets of cells, 4 cells, and that'll be fine. We'll be running some interesting temperature tests, so stay tuned for that. We'll be using our FLIR to show you where things get hot, and actually putting a whole lot of probes in there as well.
Yeah, let's go. Okay, so we needed to start off by cutting the plywood that would hold the battery case. So as we mentioned, this is a slightly different configuration to what we normally build. So it's a much longer battery case than usual. We laid out the battery cells in the configuration that they would be. So they're basically going to be 4 pairs of cells lined up in that configuration, so sort of lengthways. So it makes it quite a long, narrow case. We then marked out where we needed to drill the pilot holes for the thread bar and drilled those out. So a total of 10 holes or 10 pieces of plywood, thread bars, and then we sanded everything down to give it a nice finish and make it a bit easier to work with. And then we need to start cutting the thread bar. So we're using M6 thread bar for this project. And it was just a case of cutting those to length, roughly around 160 mils, I believe, which is about the distance between the two cells next to each other. It was about 150 mils, and then a little bit to go into the connector nuts. So we cut the thread bar down, cleaned off the ends on a bench grinder so that we could get the connector nuts on there and tied it up the thread, and then needed to start assembling the battery case. So that was just a case of cutting the tube that would go onto the thread bar to protect the cells, so if they rubbed against it, it didn't damage the cells, and then start assembling it, putting the cells in, and putting it all together.
So the basic construction of this is really, I want to put the floor in now, but just a few notes on that. I'm going to be screwing through into this plywood between the cells. What you really, really don't want to do is to actually screw into the aluminium on a cell. So you have to be really careful that you don't do that. So I've got the bottom, I've marked the holes. It's surprising how easy it is to screw into plywood, but the trick with that is that you have to drill a pilot hole. For the most part, if you just screw straight into the plywood, you're going to split it. So to that end, I've got a 2mm drill, and I'm going to, as soon as I can see where I've actually marked these holes, so basically, let's see, it's about there. So drill the pilot hole, put the bit back on. In this case, I'm going to use a 40mm screw, which is going to take it to about there. And because this is the bottom, I'm going to actually screw this right until it's countersunk. And that'll work.
Okay, so we're just about to charge this battery here. So we've got our BMS there. It's just lying upside down. We're going to turn that over in a second. I just wanted to demonstrate here. But this is how we've configured this battery. So we've got 2 lines of 4 cells each. Obviously, we are connecting the cells this way, which is in parallel, so positive to positive. And then this is obviously closed circuit, but that's the same as having this connected here. So that becomes 1 cell, 2 cell, 3 cell, 4 cell essentially. And then obviously this way we're connecting them in series. So that's our positive to negative, positive to negative, positive to negative, our outside positive there, which will obviously go to the charger and draw, etc. And then our BMS is connecting over here. And obviously there's 2 other cables there on the BMS that will go to our load and charge, etc. And then the balance leads all connected on this line, which obviously with these bridged like that, it'll balance all of the cells. So pretty happy with how that's looking. We're going to use the BMS to do a fast charge now to get the battery up to pretty much full state of charge. And then we are going to then obviously disconnect it all and top balance everything. So we're just going to place the BMS here on those rolls of tape just as a temporary solution, just to get the thing charged. It'll take probably 10 hours to charge or thereabouts because it's such a big battery bank. So connect the balance leads up and get this thing going.
Right, so top balancing is complete. As you can see on the charger, we're down to 0 current draw. This is a variable current charger. We've set the voltage to 3.65. I'm just doing a double check on every single cell. I want to be absolutely sure that everything is connected. So 3.64, that's good enough. 3.64, 3.65. 3.64, and the last one 3.64. If I check actually on the cell terminals, that's exactly what I get. So as you can see, we've done the top balancing, the final top balancing, using normal household electrical wire. This is 1.5mm wire. We can set this to a very low current, so we've set it at 5 amps and ran it overnight. We had previously charged these up using the normal BMS with the normal charger. We charged it at about 70 amps, I think, 60, 70 amps. That took about 6 hours or so, brought the whole bank up to nearly 100% state of charge. They're very good, evenly matched cells. And so running the 3.65 volt charger at 5 amps was absolutely fine on this household electrical wire. So you don't need to buy extra bus bars and make fancy things. Top balancing, if you can, especially if you can charge at 10 amps or less, you can just use normal household electrical wire like we've done here, and that's absolutely fine. The wire was never warm, so no problem carrying the current. Everything is top balanced. Everything is ready now for us to disassemble this and do the final assembly onto the BMS and run the temperature tests. So we're not doing capacity tests in this, we are doing temperature tests because we want to see that this bank on a 300 amp daily BMS can cope with between 2 and 300 amp draw at the same time.
Okay, so something went weird with the original audio on this video, but we've got the battery now fully top balanced and we've got the BMS connected up again. So this isn't the final installation because we've just put the BMS loosely just connected. Obviously, torqued everything down for the temperature test, but it's not how it's going to look in the final install. This is just so we can monitor temperature across all of the terminals on the cells and the BMS and everything. So we've got the cells all connected up as they need to be, and we've got two 25mm squared cables running to the inverter. So we're going to use 25mm squared for the purpose of this video, which is ample for the total capacity that this inverter and the BMS can cope with, so 300 amps. But when it comes to actually building the battery out finally, we're going to actually put 35mm squared cable there just because we can. On the BMS, it has 4 cables, so 2 going from the battery cells and then 2 to the load and draw. So the 2 that go to the battery cells, we've got them on each of the outer negative terminals on the batteries there. The main reason for this is just that it's increases the surface area that they contact, so splits the draw on those 2 cables essentially, and the idea is that it'll potentially decrease the risk of it overheating or anything like that, because obviously they're on their separate cells like that, which is what we think will be the best in terms of performance. So we've got a 3000 watt Guy&Dell inverter, which is what we're going to be using for this test. One of our biggest areas of concerns are these little M6 bolts on the inverter. So it literally just has 2 bolts on the terminals, so one for positive and one for negative. And that's our biggest area of concern, is that you have all of this current just passing through those 2 bolts on those terminals. But this is a test that we're going to be running, so we're going to be boiling 2 pots of water here. So the plate on the left is going to go up to 1,800 watts. The plate on the right is going to go up to 1,000 watts, and we're going to be running a total of 2,800 watts on this inverter. And we're going to probably run it for about half an hour until the water is boiled, or however long it will take the water to boil, and then wait a little while. Basically just monitoring the temperature of the cables and everything. And with it running, that's drawing 270 amps there, which is a good amount.
Right, so we're monitoring this battery, well, the whole setup, the battery and the inverter, with a fluoro camera to see if there are any excessively hot areas. And as you can see, the inverter itself, the cooling fins on the inverter, are probably the warmest, and they're absolutely fine. So when I say they're warm, I'm touching them now by hand, and they're actually quite fine. They're just slightly warm. The cables are slightly warm. Really nothing to worry about at all. These connectors, which is something that I was concerned about, are really not a problem. If I come across to the battery itself, you can see clearly the 2 negative lines coming out, and they're about as warm as my finger. The bus bars and the connections, no problem at all. If I bring it along here, you can see nothing stands out. Further on, nothing stands out, nothing is terribly hot. And finally bring it to the end. You can clearly see the two positive cables coming out. And once again, they're really not that warm. So far, when I look at everything, I am completely satisfied that we do not have a problem drawing 2.8 kilowatts. If I look at the inverter, still drawing 2.7 kilowatts on the inverter. The induction hob is running 2.8 supposedly, and hot air coming out of the inverter, well, warm air coming out, not really hot. And yeah, the BMS fan hasn't even turned on, so it's now look at that with a FLIR camera, it's really not that warm. In fact, it's fine, absolutely fine, not much heat coming out of here. So this rig is operating really well. what I see, I'm really well pleased with. To put this into the van, you get 560 amp hours of usable power running through a 3 kilowatt inverter with obviously two lines coming off the 2P system. These will be thicker cables that we actually use. We'll use 35, so I'd expect them to not heat up at all, each carrying 150 amps at the most. These are already 2 AWG, so they're pretty good. And yeah, everything is coming to a boil now. You can see it's probably our hottest thing is there, which is 100 degrees centigrade practically, coming to there. And we're about to turn the induction plate off because everything is boiling and we can't just have the water boiling for nothing. Right, let's turn them off. Fan on the inverter has come down immediately, and those are just cooling down now. Yeah, very pleased. This is going to work really well in the van. Imagine a smallish van with 560 amp hours of usable power. That's just crazy, absolutely crazy. Right, so we previously had run an induction plate, a twin plate that's 2.8 kilowatts. To make sure that everything would cope fine, and it got to the point where it boiled 2 big pots of water without any problem at all. Things didn't heat up really much at all. We then put on 2 heaters, so we got a heater down there and a heater on the table here, and set them to full blast. This place is really toasty now with all these heaters running, and we've run them for about an hour. Run this down to 50% of its capacity. Bear in mind it's a 560 amp hour, so that's a load of power that we've drawn off. And just kept on coming back and checking these cables. We haven't bothered with a FLIR camera at this stage because we know nothing is going on. And yeah, probably the warmest cables are these, which are 225mm. I'm very pleased with this. I think in terms of what we were trying to achieve, which I know I'm repeating myself, but we wanted to implement a 12-volt battery. So this is 12-volt battery, but in such a way that we can run a very heavy load off it. So the induction plate with 2.8 kilowatts. We went for the 2P4S because we have basically, it's the equivalent of 2 batteries in parallel. The way that we mount onto the separate terminals and run 2 cables coming back to the same point on the inverter. This I was concerned about, but we tightened it quite tight, and the fan blows straight over here, so it cools it down. So no heating problem there. BMS fan didn't even turn on, so the 300 amps have a fan, but I suspect they only really kick in when you're drawing close to the maximum. But yeah, this thing should, in terms of what we were trying to achieve, this will drive a 2.8 kilowatt induction cooker, no problem at all. And so we don't need to carry gas in the van. We don't need to think of gas solutions. We've got so much power. The challenge will be how fast we can charge it and replenish it. With like a 30 amp DC charger is going to take quite a long time to bring this up to charge if you flatten it. Right, so we've put these 2 bars on here. This is where the BMS is going to rest on. So they don't need to be thick and strong. They're just just strong enough to rest the BMS on, screwed by 2 screws so they can't twist on each side. We'll be screwing the BMS with very thin screws into here. We've positioned them in such a way that they're nowhere near the terminal, so they're as low as possible so we can give the BMS enough room on top to ventilate. Nothing touching anywhere, so it is perfect.
Okay, so the BMS is mounted in there now on its shelves. We've also run 2 35mm squared red wires, which are coming out here. And the reason is we're going to put 2 bus bars, one on either side here, for positive and negative, to be able to connect these easily to the inverter and then the rest of the drawer, etc. So we're just boxing this off. This side we're going to have the side come to probably about here, just to allow for more ventilation, and then the other side is going to be completely closed off, and then putting a lid on here as well. Okay, so here we are with this battery pretty much done. Got 2 big 35mm cables going to the positive there and running along the top of the battery, the 300 amp DALI smart BMS there with Bluetooth, and we've just stuck the Bluetooth module to the wall of the battery there. And then we've got a side on the side of the battery here, with 2 bus bars there and there. So the 2 cables coming off the BMS to the black to negative, and then the 2 positive cables running underneath the BMS here to the positive bus bar. We did think about putting the bus bar on the other side of the battery, just to avoid the risk of these being shorted, but we're going to be pretty careful with this, and also it just means that everything's on the same side, and we can potentially protect this to make sure that there isn't risk of shorting it. And then the other side is just a clean face. So this will be what will be exposed to the back of the van when we open the back door. So at least we know that everything's protected on that side. Obviously, there's going to be this bit of gap here when we put this lid on. So this lid is going to go on the top there, sit on that shelf that we've created. And there's going to be this gap here, which will just allow ventilation. We've got all these holes all the way down the side here as well, which will help with ventilation, but that's what the finished product is going to look like. So we just need to screw this down, and then we're going to be able to get this into the van. But yeah, otherwise, I hope that you've enjoyed watching this video, and of course, we'll be continuing the series, continuing building out the van, and we will be taking you guys along and when we actually install this and put this into the van and get the electrical system in there. So yeah, we're going to get this screwed down, and we will see you guys in the next video. Thanks for watching.